being able to open up something, figure out how it works, not worrying if you destroyed it by opening it up. It was more interesting to figure out how it works. Like I opened my TV, I learned how it works. Now I can't put it back. Something broke on the way. So TV is gone, but too bad. I learned something. If that learned something is more valuable than your TV, then probably you're a scientist or you're destined to be one.
Hello and welcome to The Frontier, a physics series where we have conversations with esteemed researchers in the domain of physics about their fields, why they do what they do, and their journey with science. Today we're joined by Professor Sunil Mukhi. He's a theoretical physicist who has worked on the theories of elementary particles and a dean of faculty at IISER Pune. He got a B.Sc from St. Xavier's College in Mumbai and a Ph.D. in theoretical physics from now Stony Brook University. Before returning to India to work at TIFR in Mumbai, he was a postdoctoral fellow at the International Center for Theoretical Physics in Italy. In 2012, he left TIFR to join IISER Pune as the head of its physics department, and in 2019, he became the dean of faculty at the same institute. Among other things, he's known for his work in supersymmetry, fundamental properties of string theories, the discovery of a new duality between string theory and M theory, and so on. Professor has many varied interests in addition to physics, including cinema, cooking, literature, meditation, and music, from Indian classical to jazz. Notably, he has even been the lead vocalist of a progressive heavy metal band based in IISER Pune. He has handled a blog where he talks about many of these things. Professor, thank you so much for coming on.
Thank you, Arnab. It's my pleasure to be here.
Yeah. Would you like to say a few more words about yourself to the audience?
No, I think you said it all. This is what I do. I'm at IISER Pune, and I'm a professor of physics with theoretical physics as my specialization. And if I can be helpful to anyone who's interested in doing physics or knowing more about physics or knowing about how physics is done, I'll be happy to try and help.
Great. So we can get into it. So I want to start with knowing why you chose physics.
This doesn't have a very, unfortunately, doesn't have a very profound answer. I was in Xavier's College doing my B.Sc, and it was for those days, it was a reasonable level of B.Sc. It wasn't anything great, but, we had teachers were reasonably kind and helpful, and we were learning physics, chemistry, and maths. Those were the subjects. But many of my cool friends who were like super smart were attracted by physics. And so it was really some kind of peer pressure that made me feel physics is what I want to do. But I think if I had just been randomly placed in kind of environment with people who wanted to do chemistry or maths or biology, I'd have picked one of those. I don't know if I would have done well in any of those. My special abilities lie more towards mathematics. So mathematics or physics, I think, is what I could have chosen.
Okay. So even after getting into physics, do you have any profound answer for why you chose elementary particle physics?
Yeah, that's a little more. Yeah, that may be a little bit more. In Stony Brook, as PhD students, we were given a year to think about what we want to do and who to choose as a PhD advisor. And certainly at that time, I was very much drawn to theoretical physics and quantum field theory, which was a subject that I really, really enjoyed. I took 2 semesters of that, QFT1 and QFT2. And I think around that, and also I was fortunate enough to have a course on group theory from C.N. Yang, the Nobel laureate, and who was the head of our department. And he's, of course, the Yang of Lee and Yang parity violation. He's also the Yang of Yang-Mills theories. That was an inspiring course. And yeah, there were a bunch of courses that put me on that track.
Okay. So looking back, what is one thing about the field that you have grown to appreciate even more?
Yeah, actually, now I'm close to official retirement age, and I feel I've only now begun to understand, to appreciate how the field is structured and how it's different to other fields. I think what I appreciate is it rewards rational inquiry. So if you're an inquiring mind, you want to understand something, this is a particularly theoretical high energy physics. It really rewards any effort you make towards understanding things. And at the same time, it doesn't put you into a very narrow corner, in the sense that the tools I use could come from group theory, differential geometry, topology, various areas of maths. And the things I work on could be related to particle physics or even condensed matter physics, phase transitions, things like that. Or they may even sometimes use physics methods to solve maths problems. So one of the things I'm working on for the last several years, and I worked on earlier, is really to address some class of mathematical problems which are not solved yet by mathematicians. And so one of the gratifications for me was that as a physicist, we published a bunch of work which mathematicians didn't know about. And then because we published them in physics journals, and then when mathematicians got to study that same topic, then they realized that we had been sort of ahead of them by about 20 years. And there was one paper which particularly described my work of 1988 as being ahead of its time. I never thought I'm that kind of person who's ahead of his time, but somehow in physics, we came to a problem before the mathematicians and they appreciated it. So that was a nice feeling.
So by contrast, what is one preconceived notion that you have dropped over the years?
Lots of preconceived notions dropped over the years. I think I think there are two or three, and I try to communicate these when I teach. One, of course, is that you have to be specially inspired to work in this field. I thought that was, I thought people like me could achieve so much, but there are people who are super genius who can achieve much more. I think I dropped that when I realized that those people who achieve more don't do it by being unnaturally gifted, but do it by being extremely patient, hardworking, and self-confident. And I'll say honestly that as a teenager and as a beginning graduate student, and even for many years after that, I think I was lacking in the self-confidence and mental balance to really take on hard problems and then work on them patiently. So there was a bit of fear I had about getting into problems, trying to attack a problem in this field. Will it be too hard? Will I fail? How will it affect my self-image? Blah blah. And I think I have to now give up all those misconceptions, because pretty much with a good training and a good mind, anyone who has addressed a problem seriously and worked on it for without flinching, without getting distracted, without being lazy, has got somewhere.
Okay. So, what was your very first experience with your work with scientific research and the field that you're working in?
That's an interesting story, and actually, it's not a widely known one. So, in 1977 or thereabouts, or maybe, yeah, 77 or 78, maybe, I was looking for a PhD advisor, and I went to a certain faculty member, and he was very popular. So, he had many students wanting to work with him at the time, and he didn't have any student right then. His previous ones had graduated. So he was looking for one, but he was very choosy. And so he gave all of us, three or four students, the same problem to solve. He gave us a paper published in a Russian journal, but in English, on supersymmetry, which is now today widely acknowledged to be the very first paper on the subject of supersymmetry, before it was discovered in Europe and the US. And at that time, because Soviet Union was a bit inaccessible, and there was this iron curtain, people didn't know about everything that was done in Soviet Union. So he gave me this paper, just 3 or 4 pages long. And he said, look, it seems to have a good idea and seems to be a precursor of the idea of supersymmetry, but in detail, what they claim cannot be right, I believe, based on what I know about the subject. So you have to read the paper and tell me if it's right or wrong, and if it's wrong, where is it wrong? And the thing is, he gave essentially no guidance. He said, we are of course allowed to consult literature, but not allowed to talk to anybody, not even him. We just have to solve the problem. So the very first thing I did in research was to be like thrown in the deep end with a paper of 3 or 4 pages, obviously not too long. So, by banging your head against it, you could obviously read it eventually, line by line. And eventually I was able to do the calculations and reproduce them. And then I found that, yes, indeed, there was a fundamental error in the calculation, but it could be corrected. And the basic premise of the paper was not wrong, but in details, it was indeed wrong, as my advisor had said. And then he asked me to correct it and also extend it by adding gravity into this system. It was a mathematical formulation. So add gravity, which these people had not done, leading to a theory called supergravity. So I did that for this work and I published it as a single author paper. And that was my first paper. And there's a peculiar corollary to this story, which I've never understood, frankly. A few years ago, I looked at that paper, like, why don't, just to look at my paper from 41 years ago. And I noticed that I had not cited this Soviet paper, which was the inspiration for my paper. And I now remember that my advisor somehow didn't want to acknowledge. He had something about Soviet Union. There was some politics at that time in the US that communists were something very evil. And for some reason, I was discouraged to quote the original paper, which I think today is a very questionable practice. So it also left me a little bit alarmed about how things are done.
Okay. So ultimately, what that paper was, if I'm right, it's 89, right? That's when you published the paper.
79, 1979.
Yeah. Okay. So how was this experience different from all of the education that came before, preparing yourself to do some work like this?
I think the way I had just done a standard B.Sc in a city college, and we were given some textbooks and told to learn some chapters. We were not taught by anybody who was actually a researcher in the first place. So here, I think IISER the IISER system makes a difference. Of course, IITs also have been doing this, that we are researchers and we also teach undergrads. I think that's very different from what I experienced. So I was never taught research methodology. I had to just pick it up myself.
Okay. So I want to come back to this kind of mentoring dynamic later. But first, I want to ask you, you just mentioned that places like IISERs and IITs are in contrast to some place like, say, TIFR, where you are not required to teach alongside your research, if I'm not wrong. So as opposed to your role as a professor at IISER Pune, which one do you prefer personally and why? Like, just personally speaking.
Oh, I absolutely prefer the role in IISER Pune. Let me though say one thing. In TIFR, one is not required to teach as such, but I was teaching at least one semester a year, sometimes two, to PhD students. But those classes were more informal, 10 or 20 students. And the students were already highly motivated and, already doing PhD or joined for PhD. In IISER, I'm able to teach students who are relatively fresh out of 12th standard, in their first or second or third year here. And it's a whole different experience. IISER students are fantastic, many of them, and I find it challenging in the most fun ways. So I just love this experience. I'm even loving it now during lockdown when I have to videotape my lectures, put them online, and then meet the students once a week on Google Meet. The questions are just as great as they always were. And actually, in some ways, it's even better, I would say, on Google Meet.
Okay. Yeah, this is definitely a unique time. So, would you say that you've been able to transfer any of the skills or anything you've learned while teaching to your actual work?
That's a good question. I don't think so because I've been teaching mostly courses not on what I work on. So there have been semesters when I was not teaching in IISER because I was also, at that time, I was not Dean of Faculty, but Head of Physics department. So I would get some semesters off from teaching. And that time I would teach shorter courses of 2 weeks, not for credit, just for, just to teach an advanced topic at 5:30 in the evening, going on till 7. Those, I think I learned things that were useful for my research. In fact, I picked those in order to be useful to my research. And that's what I would be doing if I was in TIFR. I would be doing that more regularly. But the regular courses I've taught, I think, no, I don't think directly, but I think it sharpens your understanding of physics like anything. I mean, it really, really does. I mean, every year you teach quantum theory again from the beginning, you understand it a little bit better.
Okay. So, would you mind telling the audience a little bit about, I mean, at as much of a level that you can, about your research interests?
Oh, my research interests? Okay. Uh, all right. So, there's this amazing structure called quantum field theory. It's not very well known among students. What is this? So I want to explain first what is the logic or role of quantum field theory in the general framework of physics. And when you start teaching quantum physics, probably you and students who might be watching would know that you teach something called Schrodinger equation, and you talk about wave functions, and you talk about probabilities and uncertainty principle and so on. Now that goes on fine for a while, but this whole formalism is called non-relativistic quantum mechanics. And if you now try to bring in relativity, which means you want quantum mechanics to apply uh, to particles which may even be moving at the speed of light, or you want to apply it to light itself, then this Schrodinger equation formalism turns out to be inadequate. And there's a very deep reason. The deep reason is that in quantum theory, a particle is not forever. A particle can decay or a particle can be produced, so much so that, as you must have heard, things like electrons and positrons can actually annihilate each other and go into a flash of light, or they can be pair produced from a flash of light. These kind of processes cannot be accommodated in the normal quantum mechanics that we teach. They require a more sophisticated formalism. It's surprising because you would think, well, maybe if we tweak quantum mechanics, we'll be able to explain these. But once you start having particle production and decay, you have to have a different kind of theory, which doesn't only study like energy levels of one electron in an atom, but studies processes where electrons scatter, get created, get destroyed, and so on. And that formalism is quantum field theory. So it's nothing but advanced quantum mechanics. Okay. But the problem is, once you get to quantum field theory, it was actually invented by Feynman, Schwinger, and Tomonaga under the name quantum electrodynamics. Now we understand it's far more general. Now, this formalism is so general that it applies to all of particle physics that we know of. It also applies to many condensed matter physics systems. It's a way of thinking about any system which has a large number of degrees of freedom. And condensed matter is basically the physics of materials. So in a material, obviously, you have millions of atoms. And while particle physics is done typically in a vacuum, but still the degrees of freedom associated, the modes of a particle, the possible momenta and positions are still infinite in numbers. So quantum field theory is a very, very vast formalism. And it never runs out of surprises. It admits special kinds of symmetries, and the symmetries in the past have been a good clue about the physical implications. For example, there's something called gauge symmetry, and that turned out to be a very powerful clue to find the theory of weak and strong interactions, which is called the standard model of particle physics. So I specialize more in low dimensional quantum field theory, particularly in 2 dimensions, where it can apply to condensed matter systems at a phase transition, but also to string theory and also to many other systems where something 2-dimensional happens. And I find that in these systems, there's a certain simplicity in that enormously complex formalism, and you can find new phenomena, you can find new types of behavior, and then you can look for physics problems where they might apply. So that's a very, very broad brush description of what are my research interests: to find theoretical mechanisms and effects which could apply to a variety of different physical systems.
Okay. So would you say you focus on any of these physical systems, or are you completely open to whatever it may apply to?
I'm open to what it may apply to. And frankly, I don't spend that much of my time looking for the applications, because I work in this philosophy that, well, if you publish a piece of theory and if it's good, somebody will come along. It's all published, it's all freely available. Somebody will come along and find that, well, this idea applies in this place, that idea applies in that place. It's already happened a little bit. It may happen later. It's normal in theoretical physics that if you establish a formalism or a formal result, it starts to have applications possibly much later.
Okay.
But I don't think I'm the one who'd be very good at that, because frankly, I'm not very well trained in the nitty-gritty of condensed matter systems, nor in the nitty-gritty of particle systems. But I am trained in the nitty-gritty of quantum field theory formalism. So, the world is, physics is so specialized that you can really be good at one of these things. And what I like is when, people talking to people who have a different kind of expertise, then you can sometimes find an application for your ideas.
Okay. So you did mention string theory, and I wanted to ask you, what would you say is the ultimate goal of any quantum gravity theory? Is it to unify the forces?
That's one goal. It's not necessarily the only one. We know for a fact that there must be quantum gravity because nature is quantum and it has gravity. I would dismiss any speculation that nature decides gravity is not quantum, although we can't do any experiment which proves that it is. But there's really no reason to believe that nature would treat gravity differently from other fundamental forces. So quantum gravity is a reality. So it's a reality which we can't investigate experimentally today. But I'm sure we will be able to in the future. Now, if it's a reality, it must have an explanation. You can also take a point of view that it's a reality with no explanation. People have tried that stuff before. In fact, in the 60s, people were really despairing that, weak interactions and strong interactions are a reality with no explanation. They weren't finding any explanation. Turns out that's just a defeatist attitude. The explanation is there. It's just up to us to find it or not find it. We may not be good enough to find it. So a theory of quantum gravity surely must be there, and there may be many, and one of them must be correct.
Okay.
If that theory also has the feature that it unifies gravity with other interactions, I would say that's all the better, because all the other interactions are already to some extent unified with each other. So it would enlarge the scope of unification.
Okay. So if I understand the standard model correctly, is that it has already unified 3/4 of the forces. And so anything like string theory would be aiming to unify that with gravity as well, right? So
That's
what,
exactly right.
yeah.
Uh,
So what
though
is,
let me interrupt you here just to say, we shouldn't give too much credit to the standard model. It really doesn't unify three of the four. It describes three forces: electromagnetic, weak, and strong forces, but it only unifies electromagnetic and weak. Those are actually unified in the sense that the photon and the Z boson are different combinations, or they arise within the same structure. So photon, Z boson, and W bosons are all part of one structure. Strong interactions involve different particles which are part of a different structure. You can add the two, but electromagnetic and weak are unified. So there could still be a theory that unifies everything in the standard model much better. People have looked for that. Those would be called grand unified theories, or GUTs as they are known. But now you asked about string theory. It deals with the fourth force, and it might potentially unify it with all the other three. So it might solve all those problems.
okay. So what is the next big thing in, quote unquote, next big thing in quantum gravity?
Okay, I can tell you what's the current big thing, though I'm not working on it particularly myself, but I'm following it keenly. The current big thing in quantum gravity is to understand the information loss paradox in black holes. Now, we are talking on a particularly nice day because yesterday a Nobel Prize went to three physicists, one theorist, and two experimentalists for their work on black holes. And it has sort of given a final acknowledgement that black holes, far from being exotic as was once thought, are the most common objects in the universe. It's just full of black holes. There are more black holes in the universe than people, or people like you and me, for example. So in this context, you must have heard that Hawking had proposed a puzzle that he proved that black holes generically evaporate by giving off a kind of radiation. And the puzzle was that since we can never go inside a black hole. So what if we throw some information in, and then that information, somehow what comes back out is just radiation, just thermal radiation, which apparently has no information in it except the temperature of the black hole. So where did all the remaining information go? And right now there's been amazing progress on this question. So this is the live and the hottest topic. I would say people have pretty much stopped working on the unification aspect because it has turned out too difficult. Few people are bravely soldiering on, but there hasn't been any encouraging news about unification for at least 2 or 3 decades, and people start getting a bit discouraged. But gravity, on the other hand, again, as I said, it's there, it's out there. Black holes are out there. So there must be an explanation of how black holes evaporate. It's not possible that there's no explanation. That's the thing people are working on, and they're using string theory techniques, but it doesn't entirely rely on string theory.
Okay. So how optimistic are theoretical physicists before an experiment? Like right now, we don't have access to those domains to verify any theories. But how optimistic are the theorists working on these kinds of theories that their work is correct?
Well, let me just say that, let me advertise a talk I gave some time ago in a seminar series. I think it must be online somewhere. It was called The Particles Predicted by Theory. And it was a bit of a historic tour of a few different particles which were predicted by theorists, and then were not found in some cases for a long time. In some cases, they were found in a short time. And these particles are, in particular, the neutrino, which took decades to be found, the positron, which, however, was found just in a couple of years, the Higgs boson, which took like 5 decades to be 4.5 decades to be found. And in all these cases, I would say most serious theorists had little doubt that they would be found. So I think people are very optimistic that the methods we use are on the right track, and we are learning, or we're doing the best we can given the existing experimental facts. And we believe that future experiments will not simply confirm what we are doing, but will, you know, we don't make sharp predictions like do this experiment and you'll see this. By the way, nor did Penrose make a sharp prediction in 65 that in a way he did. He said that, well, matter generically forms black holes or can generically collapse, but he didn't tell us where to go and look for black holes. He wouldn't have known then where to look for them, what size they must be, what their distribution in the universe should be, whether they should be in the center of a galaxy or somewhere else. He didn't tell us any of those things. So experiments confirmed his idea in the broad sense and sharpened it. And this is how science progresses. So there's a misconception that I tell that by doing a calculation, I tell experimenters, do this and you'll see something with probability 0.79 or something. That's not necessarily what theory does. We also tell experimenters, well, look at this and you'll find something interesting in the broad class of such events or such processes or such possibilities. And then when the experimenters find something, then we are like, okay, so that's what it really is. Now we do more theory. So it's a cyclical thing. It's not that you do theory and then it's confirmed by experiment and that's the end. It's rather theory, then experiment, then because of the experiment, more theory, then more experiment, and it goes on like that. It's a cycle.
Yeah, with that in mind, would you say there is any validity in the criticisms that people have of string theory, that it does not have any experimental evidence yet?
So the criticisms that I've read are made by different people, I think, with different points of view. I mean, it's not like there's one criticism of string theory. There are people who think that particle physics itself is a pointless enterprise because it's reductionist. It boils everything down to fundamental particles. And so what? Who cares? It doesn't, fundamental particles won't help you devise a room temperature superconductor or solve humanities problems or whatever those might be. So why do particle physics at all? Now, those people obviously also think, why do string theory at all? So then you could move on and say, well, let's discard those kind of criticisms because we think particle physics is a enterprise to understand fundamental constituents, and that has to be a good thing. I mean, to
Yeah, I
understand
mean, when
what
I say
everything is made up
criticisms,
of.
I should
Yeah.
probably specify that I meant criticisms not coming from a place of ignorance or malice. Criticisms where people like have the knowledge of like, yes, this is useful and this is, but this also requires a lot of funding, but the world also has a lot more problems. And so we've been spending billions of dollars on building colliders to have access, experimental access to these domains that these theories are making predictions in, but it's also not yielding any results yet. At what point does it become unscientific at any point to keep going?
Okay. So you use two very powerful words, ignorance and malice. So, the point is that I think the criticisms I'm talking about are not ignorant. About malice, I don't want to comment because I can't necessarily judge people's motivations, though I can suspect them. So, first of all, string theory is almost completely unrelated to the fact that Large Hadron Collider was built. It certainly wasn't built to prove or to verify string theory. In fact, it was designed and built by a community of people who typically don't like string theory at all, because string theory talks about Planck scale physics. And Planck scale is 10 to the 19 GeV, while LHC operates at a scale of 10 to the 4 GeV or 10 TeV. Completely different. So those people who design and built LHC think that string theory is, from their point of view as experimenters, pointless. Okay. The theorists who worked on TeV scale physics also typically don't work on Planck scale physics. So it's not that this collider at this expense was built by string theory or to prove string theory in the first place. Okay, it rather seems to me that because it hasn't found anything strikingly new, that it's sort of used as a kind of stick to beat string theory with. But I don't think string theorists were even part of the designing process or planning process.
Well, not just string theory. I meant
Hmm.
things like just generally theoretical things like supersymmetry
Ah.
and all of these things that people look for.
No, so now once we take the discussion away from string theory to what you say is generic particle theory, then of course we come back to the question that, well, Higgs and others proposed the Higgs particle in 1965 or thereabouts, 64 or something. And it was, after all, found at the LHC, and it wasn't found before that. And we know something of absolutely lasting value because of the LHC, which we wouldn't have known before. And this was the first priority, the first reason to build LHC was to find the Higgs, and they found it. Now, you can always say, well, it was obvious that it should be there and they found the obvious thing. It was not at all obvious. Nothing is obvious till you find it, right? Theorists may believe anything, but it's not obvious till you find, it's not true till you find it. I mean, you can't
Right.
be sure it's true till you find it. So, well, should Higgs have not bothered with that paper, and should people have not bothered to understand how the weak interactions work? If that's your view, then of course the expense was not worth it. And by the way, that has been the view of some physicists who have gone on record with it. Of course, one famous one was the late Phil Anderson, who was opposed to this, to building the super collider in the US, which, if it had been built with the design specifications, would have found the Higgs before the LHC. Okay, so was Freeman Dyson. In fact, I happened to be present at a dinner with Dyson in Princeton when he started really, sort of raving about the fact that, hadron colliders were a useless thing. And he said, I still remember it. He said, tables and chairs, all that comes out of a hadron collider are tables and chairs. What sense can you make out of it? You'll never find anything at a hadron collider. And the LHC proved him entirely and totally wrong. So there were very good scientists who were opposed to this, partly the expense, and there were other people who said that, okay, you may find or you may not find something, but the expense just isn't worth it. Spend it on materials, on medicine, on things that benefit humanity. What is this stuff which soaks up so many billions of dollars just for some abstract understanding of fine points of nature? And there were scientists, respectable scientists, who held that view. It's a debatable view, that's all I can say.
Okay. So, I mean, one thing you can probably say with certainty is when some work is wrong, right? So what is the margin of error in theoretical physics research?
Actually, it's not that obvious that you can say some work is wrong. So there has been, about Popper's criterion of falsifiability.
Yeah, Karl
So
Popper.
I'm a Karl Popper. So he had this criterion that it's good science if you can falsify it. That means if hypothetically there's some experiment which will show it to be wrong, then it's good because now it could be right or it could be wrong. So that's when it's good science. Now, probably with undue lack of humility, I believe this viewpoint is nonsensical. And I've written about it. And I'll be happy to tell you why. With an example. There's something called Fermi liquid theory. It's a way to describe certain materials, how they behave. Okay. Now, is it falsifiable? I asked this question once on Facebook and I have a whole bunch of scientist friends from around the world. And at first, a few were puzzled by my question. So I said, no, in Popper's sense, is Fermi liquid theory falsifiable? And after I asked it enough times, I must say I was initially ridiculed for the question. Then I finally got people to agree that Fermi liquid theory describes certain materials. It doesn't describe other materials. Those other materials are called non-Fermi liquids. So some materials are Fermi liquids, some are not Fermi liquids. We don't know a priori necessarily which ones are and which ones aren't until we apply Fermi liquid theory to those and find that they either their conductivities or their various properties, magnetic properties or other properties exhibit the behavior of Fermi liquids or they don't. And if they don't, we don't say Fermi liquid theory is wrong. We say, oh, those materials are not Fermi liquids. So Fermi liquid theory is not falsifiable. And in fact, there's an obvious attribute. Instead of falsifiability, the question should be, is it useful? And Fermi liquid theory is sometimes useful for some materials, and it's not useful for other materials. And I think all of science should be judged on usefulness, not usefulness in the narrow sense that it helps society, but usefulness to understand something. And I would defend clearly that string theory is useful to understand gravity. It's actually useful, and I can explain that in a more technical lecture, in what ways it's useful to give insights on gravity. And I can also say that if any other theory is more useful to understand quantum gravity, people will drop string theory like a hot potato and start working on that. And science progresses by a series of more and more useful theories.
So you've just kind of spoken against a heuristic that so many people. I mean, Karl Popper's ideas. If you can falsify it, then it is scientific. But so are you saying that there are fields in physics that have grown out of this idea, and that
I don't know if others accept my idea. This is my view. I've said it publicly. People look at me as if I don't know what it is. I've not really been engaged with people to debate it much. But I've given talks on it in India, and I don't go abroad all that much. And when I do, I focus on my research and not on talking about philosophy. But I'm baffled that first of all, Popper did not found the scientific method, right? I mean, Newton and Galileo presumably knew what they were doing without Popper's help, since they came much before him. So, these are there are some, fashionable phrases. Popper had a certain context. I actually looked at some of his work and I found the context also very strange, but I don't want to go into that now because I don't remember the details very well. But, Popper or Kuhn, they wrote about, how science is done. But the reality is that science is done by the people who do science. And the moment science turns out to be a useless way to do things, people will stop doing it. I think that's very, very simple, you know. But when there's a more useful way, I mean, right now, science is the most useful way to understand medicine, to understand technology, to understand fundamental principles of nature. So medicine, technology, and physics, also biology to understand living systems. Maybe some other way to understand living systems which is more useful. I can't even imagine what it would be, but maybe it's there. Well, if it's more useful, people will use it. People are not fools, at least in the long run. In short run, people can be fools, but in the long run, people will pick up whatever is useful and start using it. So
So,
I think this
yeah.
and I think falsifiability, particularly, it's very appealing if you think about it for 5 minutes. But I think it looks like nonsense if you think about it for 15 minutes. It's just a matter of how much attention people give to it.
So I mean, there have been people like Feynman who have said outright things like, if it disagrees with this experiment, it's wrong. These kind of quotable things that they've said, it's kind of in line with what Popper's ideas were, right? And so I'm just going to like
I,
stick on this philosophy of science discussion for a minute more.
sure. I think Einstein, or was it Einstein or Dirac who said, I think maybe Dirac, who said that if experiment disagrees with theory, then the experiment must be wrong.
I'm not entirely sure.
You look it up, look it up. There is such a quote. I think it might be Dirac or it might be Einstein. But the point is, okay, Feynman, Dirac, Einstein were all very good scientists, but they had quite opposing views on how should be done. And the lesson we learn is that good science is quite independent from people's views of how science should be done. It's a kind of humility. We whenever we talk about how something should be done, like science, we are talking at a meta level. We are talking above the level of the people who are actually doing the science, and we risk injecting a lot of prejudice into it, even if we are the person doing science. Like I'm a scientist, you're a scientist, but my meta thoughts and your meta thoughts may be contradictory, and both may be very limited, but our science could be very good. So when I read Feynman or Dirac or Einstein, I want to know what science they did. I don't really want to know too much what they think about how science should be done, because I don't see any reason to trust them.
Okay, so you're saying science is not as debatable as the philosophy of science is.
I think so. Yeah, it's a peculiar statement, but I think it's true. I know. I mean, a lot of thinkers, modern thinkers, would get on my case for saying this, but I don't mind saying it. If they get on my case and I have to rethink it, I'll rethink it. I might change my mind. But from what I know, all this business about saying how science should be done has never ever influenced how science is done. I've also known living physicists who have told me or announced how science should be done. And what I found is that those announcements, that those views may have worked for them, it may not work for others.
Okay. So, I mean, on a personal level, if we come back to that, as a theorist, what exactly does the concept of truth mean to you then? Like, do you, when you're working on something like string theory, do you believe that there are strings that whatever you're working on?
No, because nobody believes that string theory must be true, because it predicts certain behavior at Planck scale that we are completely ill-equipped to test right now, because we have no access to the Planck scale. By the way, all theories of quantum gravity will predict some behavior at the Planck scale, which we can't test right now, not only string theory. So any theory of quantum gravity is necessarily, to large extent, untestable right now, as far as we know. Uh, what I
again, I
believe
meant
is
string
true
theory
though.
as an example, not like specific to string theory.
Okay. So I'll tell you what is truth for me. If I start with some assumption, which is embodied in an equation, and from that I do some calculation and reach a conclusion, then if the calculation is correct and the assumption is correct, then the conclusion is correct, right? So start with an assumption which is correct, calculation which is correct, then the conclusion is correct. But the conclusion may be something new, and so that would be a new form of truth. Now, of course, the calculation may be wrong. That's a risk. But obviously, I and any theorist will struggle as much as they can to make sure their calculations are not wrong. Now, the assumptions could be wrong. And for that, I would say as a theorist, well, too bad. Those were the best assumptions I knew at the time I did the calculation. So the result is still a truth from that assumption. If the assumption isn't true, too bad. Maybe that calculation which I did can be employed with different assumptions and will lead to a different truth. So maybe I have still influenced some future scientists to do something in my way. That's good enough for me.
So in a nutshell, you're saying that you can broadly say that in theory you have assumptions and calculations, and so if both of them are true and useful, then it is what people usually say correct or true.
So even if they are not useful immediately, it's still correct or true. After all,
Yeah,
mathematicians have results which can be very, very not useful at the time they are found. Even simple things like factorization of numbers into prime factorization of numbers was a kind of quintessential non-useful activity for mathematicians, number theorists in the up to the early 20th century. Hardy from Cambridge even proudly said that what he was doing was useless and that was part of
yeah.
the appeal. But it turns out that your internet banking works because of that. How Hardy didn't know that, so useful is always a bit later. But yes, assumptions and calculations, if they lead to some conclusion, that conclusion is true within the assumption.
Okay, okay, makes sense. um so like you mentioned, Penrose just got a Nobel Prize for his theoretical work in black holes. So what is like a valid measure of a theorist's contributions then?
That's a difficult question because the Nobel Committee has set a valid measure from the beginning that it has to be something which is experimentally confirmed. So I've studied Penrose's papers quite a long time ago, and I haven't perhaps gone through the recent last decade of data, much of it coming out of black hole collisions or other gravitational waves or other observations. But I believe that the Nobel Committee must be satisfied that now we know enough experimentally about black holes to be sure that Penrose's proposed mechanism is operating. Having said that, I very much doubt, I don't know that there's one concrete formula of Penrose that's really, really tested precisely. I'm not sure of that. Again, I've told you, it's not that, there's one day when an experimentalist tests your formula. It's a progression. You know, Penrose's work is obviously well confirmed, but well confirmed is a subjective uh, expression. It can surely be better confirmed. There may even be experiments in future which disagree with his calculation. There may even be an error in his calculation. Who knows? I mean, these are all things that evolve and develop. So to get back to the original question, the Nobel Committee gives you the award only if you're, for as a theorist, only if your theory is confirmed substantially by observations. But there are other awards, for example, the Fundamental Physics Prize instituted by Yuri Milner, which doesn't have this requirement. And Ashok Sen, as you probably know or you've heard of him, has got that prize, richly deserved for theoretical work, which on duality, which I know well because he's a good friend of mine and because I've also worked in the field and because I've discussed it with him for years. And it's superb work. And we don't know if it will be useful or not. We don't know if it will be confirmed, quote unquote, or not in some context. But we didn't know that about Penrose's work either.
So honors aside, just Can you say objectively, is there any measure that of a theorist's contributions, any fair measure?
Yeah, it's difficult. I mean, of course there is. I would say that, if you add, so you're working within a body of knowledge. Have your papers added something to that body of knowledge? The highest level would be that you created a body of knowledge which was just not there before. That's the highest achievement. You created a whole direction which people hadn't thought about. Lower levels, but still very high and very important, are you added something to the community knowledge of that field, which is significant, which people use. That's why they look at how much your work is cited. It's become a game nowadays, but citation is a measure of impact of your work. Unfortunately, it has also happened that there were great papers which for the first 20 years after being published, they were not cited at all. And then 20 years later, the citation curve just went up to the roof. So if we judge whether to promote a scientist based on citations and they don't have any, we might miss something because they may have written a fabulous paper and the confirmation that it's important is yet to come. But by reading it, you can get a sense of how deep and how solid it is. So, depth of theoretical work you can understand by reading it.
Okay, so
But
the
then
measure would
obviously
be,
that's objective.
yeah. So then you're saying the measure would be mostly intangible. It's not just something that you can
It's
chart
not
people
something
and say,
you can quantify, and people give undue importance to what they call high impact journals or citation index or impact factor and all that blah blah. That's because people people have to do assessments. In a university, you have to do somehow mass scale assessment of your faculty. It's an ugly thing though. Unfortunately, academics just doesn't lend itself to that. And then they find some formula and then everybody blindly follows that formula. And that's very annoying and it's very wrong sometimes.
so
Yeah.
we have sort of come to the topic of academia, I would say. So I want to ask you one thing. Do you think Galileo was a victim of peer review, bad peer review?
Where was the peer review? Who were the peers?
I think that would be the church, right?
But not his peer. Peer has to be somebody who is as skilled as you in science. Obviously, the church wasn't very skilled in science, which is why they made a fool of themselves and they had to apologize many centuries later. So those are not peers. There is such
Yeah.
a thing as bad peer review, but that wasn't it.
Yeah. Okay. Yeah, I just meant that lightly, but the actual question for me would be: is can peer review, do you think, in some cases, breed orthodoxy? Because I know you've been the editor of the Journal of High Energy Physics since its inception, and so I think this would be an appropriate question for you. Do you think it's possible that these systems can breed orthodoxy?
Yes, I think so. I think the answer is yes. But I would say that even before, I think it's not so much journals. So people might tend to blame journals for that. But I think orthodoxy is bred. So there is a problem of breeding orthodoxy. I believe that. And I think that problem originates within the university system or the research institute system, where you are surrounded by people who believe a certain thing about the field you're working in. And then, and also the people around you believe disproportionately that something is important, something is not important or less important. And you may believe otherwise, and then naturally you get deflated and discouraged if everybody around you is there's a peer pressure. Literally here we are talking of peers to believe otherwise. So let me give you an example which sometimes comes to my mind. So in 1997 there was a landmark paper called the ADS CFT, about so-called ADS CFT correspondence. This is a phrase that many people have
Yeah.
heard
Yeah.
by a brilliant scientist called Juan Maldacena. Now, without going into what he did, which was spectacular, he considered gravitation in space-times, which are not the usual Minkowski space that we were thought to live in, but which are anti-de Sitter. So they have a different kind of curvature. That's basically what it is. There are also spacetimes which are de Sitter. Okay, de Sitter has a positive cosmological constant, anti-de Sitter has a negative cosmological constant, Minkowski has zero cosmological constant, just to put it. And these are the three broad classes of spacetimes. Now, until that time, before that time, obviously many people had worked on de Sitter and anti-de Sitter space gravity, but those works were largely considered uninteresting, and most people were working on Minkowski space gravity for two reasons. One, observation seemed to tell us that the cosmological constant was zero. This only changed in the last couple of decades. Second, theory seemed to be very pretty in Minkowski spacetime. Actually, it turns out theory is pretty in Minkowski. It's also pretty in anti-de Sitter. It's less pretty in de Sitter, just so happens. So Maldacena made a discovery about a gravity theory which a few people knew about before, but when he made his discovery, most scientists working at the time didn't really know the physics of anti-de Sitter spacetime. And now, today, you can practically not get a PhD in gravitation unless you know the physics of anti-de Sitter spacetime, because it's one of the most exciting things. So, but there was never any good reason not to study anti-de Sitter spacetime. It was always very, very interesting. Hawking and Ellis wrote about it in their famous textbook. It's there, but it was never emphasized. It was never something where, working on that, you would get a job or something. So until these two things came along, a theoretical revolution, but also an experimental revolution, which says, look, de Sitter is the correct thing, not Minkowski, not even anti-de Sitter. So peer pressure, I think, prevented people working in the direction they might have worked in before 97 for these two reasons. And well, uh, what can you say? I mean, there's the other problem is people who go against peer pressure might also be doing real nonsense. There are people who do nonsense and claim that it's original and it's against peer pressure. So that's also not true.
Yeah, I think
So,
it's called the
it's a
Galileo
problem, but
fallacy. Yeah,
huh?
I think there is a
Huh?
term for it. It's called Galileo fallacy. When people do that, is that they think,
Is that Galileo fallacy? I'll tell you another version of it. Somebody once commented that, just because Einstein did poorly in school doesn't mean that everyone who did poorly in school will be Einstein.
yeah. And I mean, I think ironically, I don't think Einstein did poorly in school. That's just a myth
Yeah.
if you look at his grades.
Well, there are stories about that which people like because it makes them feel better.
Yeah. So I want to move the conversation into sort of giving advice for someone who's moving into an academic career. If someone is trying to judge whether an academic career is the right fit for them, what are some personal traits that can indicate that it is?
You enjoy knowledge. You're curious. You're full of curiosity and you enjoy satisfying your curiosity. You have that stability to enjoy small bits of knowledge. You don't say, well, I'm curious about the whole universe, and if I can't answer that in 2 days, then I'll be depressed and never work again. That kind of overwhelming curiosity is not curiosity, that's actually a kind of laziness. Like, can you please package the universe for me in few lines? Then I'll go away and watch some movies or something. That's not curiosity. So your curiosity should be broad, but your pleasure in getting it resolved should come from little bits and pieces of knowledge, because that's the only thing we have access to in our lives. None of us, by and large, does something so transformative in our lives. Some do, most don't, but we all get pleasure from the little bits that we added and also the little bits that we learn when we read. So that pleasure, that if you feel that pleasure or you think you would feel that pleasure, then you're a right fit. Now, I'm talking from a theorist perspective. But I know a little about how experimentalists think also. Experimentalists above all have to be good with things. They are looking at systems. Could be an amoeba, it could be a bacteria, or a virus, or it could be a molecule, or it could be an atom or a laser. So these are all things. Of course, there you must have the joy of tinkering. Even theorists tinker in a way, but experimentalists have a real, there's a real knack of tinkering, being able to open up something, figure out how it works, not worrying if you destroyed it by opening it up. It was more interesting to figure out how it works. Like I opened my TV, I learned how it works. Now I can't put it back. Something broke on the way. So TV is gone, but too bad. I learned something. If that learned something is more valuable than your TV, then probably you're a scientist or you're destined to be one. Having said that, I don't advise everyone to go and do that.
Right. So, what is an advice that you would give someone who's sort of conflicted about whether academia is for them?
I don't know what advice to give if you're conflicted, because one problem with conflict is that it'll always be there. Like even I could ask now at the age of nearly 64 whether academia is good for me. You can always have that. If I have to be very honest, so I recently during lockdown, I acquired an electric guitar. Because I'm interested in rock music, and that interest has grown in the last few years thanks to this band in IISER, now possibly defunct because of lockdown, but it was an experience of a lifetime. And I keep every day I ask myself, am I more interested in this electric guitar or in physics? So, you can always have that. So my answer is I'm interested in both. But I think the electric guitar is giving me more of a thrill because I'm learning much faster than I'm learning physics. Like I already learned a bit of physics, and now whatever I learn is, small additions every day. But guitar, I knew very little, and now since June, I think I've learned a lot. So I'm very thrilled by it. So I figure, okay, one is my profession, one is my hobby. That's good enough for me. Now, if you're a young person about to start and you're like, do I want to be an academic, or then it's important to know what are the other options in your mind. I want to be an academic or a painter or a software person or an industrialist. Then, you're talking very different careers. And I don't know how to help somebody pick between those. I think my view of academia was always from the moment I saw quote unquote professors, I was like, yeah, I think I want to be that. I didn't have any conflict on that part. I
Okay.
really don't know what to advise. I do advise. I think parents often talk people out of it, by the way. And I would advise, but I was lucky my parents didn't try to talk me out of anything. But I would advise people, if you think you're strong, you can convince your parents of the value of what you do. I know a lot of people from all kinds of backgrounds, including very rural, including very poor families, who have talked their parents into letting them do what they do, and they're doing absolutely great, and their parents are thrilled with them now.
Right. So there is some cynicism that people adopt when it comes to foraying into academia when you're not born into an academic family, that you won't have the same level of success that someone, say, who has been kind of born into a very academic family and was almost nurtured into being a successful researcher does. Have you seen this to be true in your experience?
Certainly, being born in an academic family is a huge advantage. Having said that, it's also true that some of the most brilliant scientists known, their children didn't become scientists at all. Sometimes they did, sometimes they didn't. I don't come from a strictly academic family in that my father was a lawyer. I don't know if you would call that academic, but I think it's not exactly. But he had a great love for academic study within law and also other things. My mother was a teacher, so I guess, yeah, she was an academic for sure. And it helped. But I know people whose parents were farmers who became academics. I don't see that it's the end of the world. It's, you get a head start if your parents are academics, but it cancels out in the end, I think.
Okay. So coming back a little bit to your field, that is theoretical physics in general. Um, how competitive is the field to navigate as a career? Does one need to have some kind of well-known advisor or some kind of mentor to help them understand what is a useful problem to work, for example, in the field, or any other kind of any advice that you would have for navigating this competition?
Yeah, my survey of this informal survey, like from what I know, is that having a good mentor is everything pretty much. Having a good mentor sets you on the path. All the people I know who are really successful, almost all, I'll give. Um, so I had a difficult time with I had two mentors, PhD guides, and it was a bit difficult time. And I would say that really did affect me negatively, and I've always felt that. I know one or two other people who were in that situation who still managed to struggle through, but the bulk of people I know had very good mentors, and that uh, through that mentorship, they really saw their future forming and built up how they would be. So yeah, having a good mentor is almost everything. If I have to, if you go the other way and say, if I could make a list of all the very successful physicists I know who have not had a good mentor by a reasonable definition, it might be less than 5% of the total.
Okay. So when it comes to just learning science in general, would you say one should focus on like there have been people like I think the Nobel laureate Rainer Weiss, he keeps talking about this thing, the apprentice system, and he said that if you go to, like, to quote him, he said, go to college if you want, but what's most important is that you sniff around and you hunt around and you find a way to get some kind of exposure, real world exposure with science. Would you say this kind of approach towards, uh, I guess this is more of a sociology of education question, but this kind of approach that if you want to learn something, you start with a tangible thing, that question that you want to answer, and then you go down and kind of, instead of a top-down approach, you go bottom up, and then you learn all the theory that's required. Or would you say one should be very linear, and or does that depend on if you're doing a theoretical career or experimental career?
It depends on which type of science you're doing in the first place. Today, probably we are talking about physics, but for example, in biology, it may make very good sense to do this lateral kind of thing. In experimental physics, it may make some sense. In theoretical physics and mathematics, I feel it would make no sense. So I think in theoretical physics and mathematics, I think I don't know anything better than the linear approach. And I get approached by students all the time who have just joined IISER maybe in their first year. And they're like, sir, I want to know string theory right now. And I'm like, calm down, learn classical mechanics, statistical mechanics, electromagnetism, thermodynamics, quantum mechanics, and then quantum field theory. And then we'll talk about it. And this will take you 3 or 4 years. They're like, no, but my friends and colleagues are all doing research already. So turns out the friends and colleagues doing research in first and second year usually are working in a lab. I'm not minimizing in any way working in a lab. That's very important training for experimental physics. But it's easier to go into a lab and do some work before you understand everything that's going on. And hopefully by being there, you start to grasp what's going on. But theory just doesn't work like that. I just don't think theory works like that.
Okay, so you're saying the best thing you can do if you really are kind of impatient is just learn the theory faster, right?
Faster and better and better. I tell students this all the time. This is actually one of my most common conversations in IISER. They're like, well, they're only teaching me elementary things in quantum mechanics right now. What should I do? I want to learn quantum field theory and string theory and gravity. So I say, instead of doing all that, take the elementary things they're teaching you and get more depth in those things. If they've taught you one aspect of harmonic oscillators, there are 100 more things about harmonic oscillators that they don't have time to teach you in the semester. Go look them up and learn them. So build your depth now rather than your breadth of knowledge. And don't try to go for advanced knowledge in a hurry. That's my standard advice. I don't know how much it works in practice, but then when they ask how to build depth, I say, well, take a textbook that you're studying and solve all the problems in it. Because you'll never be assigned to solve all the problems in the textbook in your course, because the course has limited amount of time and limited time for the teacher to grade your quizzes and all that. I said, if you're that motivated, do more problems, solve them.
Yeah, I think there have been many discussions on this. Again, this is more like a meta thing that different scientists have different opinions on. So someone like Feynman has said that if you want to do something like that, you should probably have some kind of. I mean, the reason he talks about why he switched from mathematics to physics is because he wanted some kind of tangible goal, like somewhere he was actually heading, in a way. And so, yeah, and then there's like a traditional European way that I think all of us in India also have kind of adopted in our education system, is that just be as linear as possible. But do you think it can lead to some kind of, for the lack of a better word, suffocation in people if they don't see where they're heading and it's not obvious to them?
They're free to read Wikipedia and find out where they're heading. I'm not saying don't read popular science or don't read about, for example, you can read magazines like Physics Today or whatever, and figure out where science is heading, and appreciate it at that superficial level. So you're reading about advanced science at a superficial level, but you're reading about basic science at a deep level, and you're studying it. This combination, I think, is good. You have your motivation from the superficial reading you're doing. You can say, wow, unification of forces sounds great. It's something that I'll think about after 3 years, but it sounds great in the meanwhile. And then you keep looking in your studies for, when you can start thinking about those problems. All fine. But not trying to open chapter 1 of a string theory textbook just because that also, again, you have no idea where you're going. You're just doing that because it's a buzzword and it sounds very cool and everybody's talking about it. That's not a good reason to do things.
Yeah. Okay. So that's definitely a lot of good advice for people at once. So I want to move into this very slight short tangent. I want to talk about like science communication. I know you've been involved in uh, various science outreach initiatives. I suppose this would also be one of them. So like we have had excellent science communicators like Carl Sagan, who do what they do to the end of inspiring like a whole generation. At least I can speak for myself. Um, do you think it is a responsibility of a scientist itself, of all scientists, irrespective of their fields, to communicate their own science in a positive light? Suppose we were in some kind of utopia of ideal science, is it their responsibility or someone else's?
No, very much their responsibility. Who will communicate it if not scientists? I certainly wouldn't want someone else communicating what I do. They might communicate it wrong, or communicate it less accurately, or or miss the essential points or something. Very much the duty of scientists.
Yes, I mean, again, I should have specified to outsiders. Maybe that would be a
Yes,
better
yes, to
question.
outsiders. To outsiders. I mean, let's agree that science should be communicated to outsiders. If we agree on that, then obviously the ones doing it should communicate it because they will communicate it best. Having said that, not all scientists are good communicators. There are even some Nobel laureates um, who are some of the among the worst teachers in the universities because they can't be bothered to communicate in that way. So I think it shouldn't be the same amount of work for everyone. Those who can do it should do it more. Everyone can learn a little bit how to communicate science. It requires a different skill from doing science. This requires an empathy to put yourself in the head of a person who is not a scientist. You have to
Okay.
know what they understand, what they don't understand, what's confusing them, what's bothering them, and then you have to address it.
Okay.
That
And would you say these are the skills that you kind of obtain through teaching as well?
definitely you certainly improve this skill through teaching.
All right. Yeah. That sounds really great. So we are nearing the end of this conversation. So I'd like to come back to you, and I just want to ask you. You have many varied interests. If you weren't a physicist, what is the first thing that pops to your mind that you probably would have been?
Music, musician or music theorist or music scholar of some sort. Actually, I think might be more interested in that than in physics, and I never realized. I mean, I always knew that, but I never, in the time when I chose a career, I never knew that music could be a career. Like, what's the career? If it Because I was interested in all kinds. So if it was Hindustani classical, which I actually studied for 7 years when I was in school and college, But where was the career in that? I mean, my teacher, poor fellow, was a wonderful person, but living in rather poverty and in a very distant suburb of Bombay, and by no means leading a very ideal, appealing life. And he was a very good sitar teacher. Poor man is no more now. So, unless you're a celebrity like Ravi Shankar or Vilayat Khan, where are you going to get with that life? Hmm? So, you need another career. Now, in fact, most young Hindustani musicians do have another career. Many are chartered accountants or something, and then they do their classical music as another career. So, it was a bit daunting at the time. What else in music? I didn't even know that music theory or musicology are careers in academics. I actually don't know many places in India which have them. IISER doesn't have music theory or musicology as fields in our humanities department. I don't know if some IITs do, but times have changed. There was no way of making money by being a YouTuber in those days because YouTube didn't exist, nor did the internet. Rock music was totally out. I mean, what are you going to do? How much audience are you going to find in India? Now you might find more. But even now, possibly it's not clear how many rock bands really make a career out of it. And again, how many do other things. So music has always been problematic for me in the sense I couldn't visualize a career. But if I had been growing up in a developed country where there was a solid career, I don't mean luxurious, but a solid academic career, I would have certainly liked to look into that.
Okay, definitely sounds pretty cool. So right now, how is a day in your life during the pandemic? And is it, as a theorist, is it really different from how it was um, before?
The first month of the pandemic, when all of us were feeling a sinking feeling of panic inside, but paradoxically, it was the best month for me as a theorist because nothing was going on. Nobody had yet figured out how to hold Zoom meetings, so all meetings were on hold. Everybody thought everything will resume in a month or two, so it was a month or two of a break. So in that break, I thought, wonderful, I can sit and I can do my theory patiently. And I had long days doing theory and I really enjoyed them. Teaching had also stopped. Then all the misery came back. I'm only joking. But for example, then we went back to online teaching. So that was a whole new thing to learn and it was time consuming. Then Zoom meetings restarted. Now as Dean of Faculty, I'm constantly on Zoom meetings. It's becoming absurd now. Every week I spend hours on Zoom meetings in, hirings, promotions, all kind of other things. So, my head is kind of fried at the end of every day. By this time, I'm kind of ready to give it all up and relax. So yeah, it's not now I feel somehow I feel work atmosphere going to work would be nice when it comes back. And in March and April I was kind of liking it, but since then I think I feel it's too packed. There's too much going on and it's too, I don't know why. I really don't know why it's so packed, but it is.
Yeah, I hope things do get more relaxing very soon. And we are nearing the end of this discussion. So, what is the one piece of advice that you want the viewers to walk away after watching this?
Do your thing with passion and self-belief.
Yeah, that is a great note to end on. So, Professor, thank you so much for joining us today for this wonderful session, and thanks to our audience for tuning in. We hope to see all of you in our future episodes.